Once again, I'm Aglaia KONG. Thank you for giving me the opportunity to share some of the challenges and opportunities that when we're using RISC-V to build SOCs. So just a little bit of background, I guess I don't have to mention it to all the audience here. How fast is RISC-V enhancing and advancing around the world? We've been seeing the RISC-V community has been growing tremendously in the past couple of years. As I start looking into RISC-V about 4 or 5 years ago, compared to what we are seeing right now, the progress we make is super amazing. And many of you also know that besides, a lot of companies joining the RISC-V Foundation, the RISC-V chips are also adopted in a lot of the markets worldwide. And so number of chips using RISC-V has been growing exponentially as well. So from our research, what we are seeing is that a lot of people are talking about RISC-V and using RISC-V to build SOCs. However, from the market study or for the market we are observing, many of the people are using the RISC-V CPU architecture is to build using it to build MCUs. So the definition of MCU is about, it's a micro CPU, which clock speed is about anything less than 200 megahertz. And in generally, it runs the real-time OS, and price is very cost effective. And the process for it is about 40 to 90 nanometers. And we've been seeing this market growing exponentially worldwide. And also in China, we're also seeing lots of companies using the building MCUs based on the RISC-V architecture. So far, other than the MCU market, we are trying to look into the middle tier or high-end market leveraging RISC-V. In that space, the number of companies working on it is a lot smaller. And especially on the high end, there is only very few companies. So we are trying to understand why. So I think that, in the next couple of minutes, I'm going to share some of our observations on the difficulty and the challenge of building RISC-V SOCs for high end. So we think that in order for the RISC-V SOC to really get traction, especially for the high end, a couple of things we have to look at it in a holistic manner. First of all, is that people need to be accepted that RISC-V is a viable architecture for their applications. So that is something that, we have to make sure that companies leveraging RISC-V is comfortable that this ecosystem and then all the tool set around it is as easy as the ARM-based architecture. So I think this is something that a lot of people are looking at and worry about it. Is there, the market mature for RISC-V yet? Can I build applications on top of this architecture easily? So these are something that we encounter. And then another thing is very important is that what kind of market is going to accept RISC-V based SOC. So unless, we can address all these 3 areas, it will be a big challenge for us to ensure that RISC-V can be widely available. So based on all these, one area that we identified that seems to leverage RISC-V quite well is the industrial IoT space. So let's look at, how we can be successful in the industrial IoT space based on RISC-V. For the industrial IoT space, I mean, what we are seeing is that it's not as simple as you just build a SOC, just leveraging on RISC-V. We find that in order for us to be competitive and also differentiated and also attract the customer to use RISC-V based SOCs, we have to add a lot of different type of computing capabilities. So for example, in this space, customers are pretty used to use ARM-based SOCs. In order for us to compete, if we added, other type of capabilities to our SOC, for example, we added GPU for graphics, DSP for signal processing, NPU for deep learning, and then VPU for codec, etc. Then in this case, when we build this SOC, we are start differentiating in a couple areas. First of all is that RISC-V on its own is very power efficient. So for the industrial space, especially the area which is very power conscious, RISC-V win. And then in addition, because our SOC also contains all these GPU and DSP type of capabilities, we can offload a lot of compute-centric workload from the general compute unit of RISC-V to these vertical specific compute environment. And we in a way that we increase the speed of processing and also at the same time reduce the power. So this is one area that we find that we can make a difference on building a SOC that which leverage different type of heterogeneous processing and capability. And then the second area we really need to enhance and also ensure is that in our SOCs, we have to have a lot of security features. So because in the industrial IoT space, security and reliability is the most important thing to be aware of. And so making sure our SOC contain, as good as a security feature and ARM architecture contained, and also more, will provide us enough differentiation to win in this space. So particular feature, like make sure that each one of the SOCs has a unique ID, which ensure, this chip cannot be mucked around with. And then have the capability of root of trust and secure boot. And then that will ensure that the chip cannot be tampered with. And then in addition, if we can also add the acceleration in RISC-V to be optimized for blockchain, then we can use blockchain to ensure the data integrity and ensure the data is secure. So all these secure capability, if we can include it in our SOC, then it will further differentiate and also allow the customer to use the RISC-V based SOCs. And another thing that we find in the industrial space is very important is that some of the industrial use case is quite simple. So it can run really well in an environment just using real-time OS. However, a lot of the application needs a full-blown Linux to run really well. So in a way that if we can design a dual type of OS architecture, then that will allow the user-based application migration into RISC-V becomes a lot more easy. So one of the example will be like if we design a SOC to have M plus SMP, then in this case, whether the customer is application is based on just a regular C application, or that a full-blown Linux application might require a AI framework, or might require to run on a VM or to run on Docker, it can all be done. So this is something that we feel that if RISC-V based SOC has such a capability and a dual core OS architecture, it will be really differentiated compared to the ARM-based OS. So, and then another thing that, I guess to all of you is super important is that even we spend a lot of time building state-of-the-art SOCs, if we don't have the proper RISC-V software stack to come with it, it's still not be sufficient. So for us, what we are finding is that before, when you are building a application just on top of an MCU or a simple IoT application on top of a RISC-V MCU, actually the software stack is very simple. All we have to do is to have the RTOS running, and then our IoT application can run on it quite easily. So the adoption and migration is quite simple. However, if we are trying to move it up to a more advanced edge computing type of environment based on RISC-V, then the software stack become a lot more complex. So for example, we have to support a lot more softwares. And then we also need to support a lot of software on top of the base software. So the example could be if my application is based on TensorFlow AI model, then in this case, I need to get the TensorFlow framework running on my RISC-V stack first. And that probably depends on whether the Linux I'm running on is really optimized for RISC-V. And that's one example. Another example could be my application is running in Docker. Then is Docker microservice framework running on RISC-V? If it's not, who is going to put that component onto RISC-V? So when we are developing a high-end RISC-V core for edge compute, what we are finding is like peeling off an onion. Every time that we try to get something working, we find that, oh no, we have to get more stuff running, and we have to get more stuff running. So I think that this is something that we all have to come together to make sure there are a lot of open source and a lot of commercial software is being migrated and optimized on the RISC-V environment. The more we can get it working, the more we are making sure that they are open source and well supported, then the easier and faster is for people to migrate onto a RISC-V platform. And also, in addition, other than the tool and the open source I mentioned that have to get it working, it's also important to make sure that we have the common software supported in the RISC-V environment. Because for software developers, they just want to, go start programming, and they won't care. The underlying architecture, CPU architecture is x86, ARM, or RISC-V, because to them, they are writing a software running on top of a compiler. So if the adoption for just getting their software, the programming running, and then it will also prevent people from using RISC-V. So we believe that, software tools like Go, Rust, and Mono should really be optimized and run on RISC-V. And that will help a lot of software developers to start developing on top of this RISC-V platform. And in addition, as I mentioned, I really believe that RISC-V architecture is super good and helpful in the industrial IoT space. And to support industrial IoT, one of the thing we have to get it running and optimize is Edge AP. So it will be really important that we have support tools like EdgeX and get this environment optimized for RISC-V. So I kind of share, our observations, and then what we believe that in order for us to do a advanced RISC-V edge compute SOC, what that might need to do and how we can be successful. So let me also introduce a little bit of components that we have built as part of LeapFive. So for LeapFive, I've been focusing on the industrial IoT space for the past 3 years. And so this is one of the CPU core and SOC we just deliver. So it's a Edge AIoT core. It has 4 RISC-V 1.8 gigahertz cores running in this SOC. And we also include the GPU, NPU, and with 4 TOPS acceleration and all other capabilities as I listed here. So it is a pretty advanced Edge AIoT gateway that people can be used to build different type of applications. So other than all the compute capabilities, since we are going after the AIoT space, so we also added a lot different type of connectivities and also support many different protocols. So then the customer can leverage our SOCs to build, for example, a gateway for self-driving cars for the robot, and also use our SOCs to build components for a drone to inspect power grid, or build components for energy gateways to dispatch the energy in the most optimized way. So these are the capabilities and IP we had included in this SOC. So as I mentioned before, in order for the SOC to be useful, we require very thorough software stack. So since that in RISC-V, the software stack is kind of fragmented. So in a way, in order for our customer to adopt our SOC, we have to provide a full stack. So I have lots of engineers focusing on providing a optimized Linux distro to our customer. So this is our software stack. So in our software stack, we include the optimized Linux, and also come with the framework of IDE, compiler, EdgeX, and then a bunch of AI frameworks to optimize for AI. And then if customers need it, we also help them to develop BSPs, so then their application or solution can be run optimally on our SOC stack. And so we had successfully tape out and bring on the chip. And so far, our use case is around these 4 industrial verticals. They are energy, logistic, smart city, and smart factory. So it is quite cool to see, RISC-V being adopted in a very mission critical environment. So I'm very proud of what we had accomplished. And also I'm hopeful that can see that RISC-V community is getting more and more mature. So I'm looking to working with all of you and see what we can do together to make RISC-V more ready. That's all from myself. If you have any questions, please let me know. Thank you.